Okay, let's go for the next topic. The next topic is the electric field. That's the symbol for the electric field. Now let's try to derive a formula for the electric field and also how it behaves when we have a positive charge and negative charge. Okay, let's try to find the electric field of a positive charge. Imagine this is the charge right here. Now, to find the electric field produced by this charge, we need another charge to detect it, right? And that charge by convention is the positive charge. We have another positive charge right here, and this is by convention called the test charge. Test charge, which is positive again by convention. Great. Now let's see what happens when we place a charge, positive charge, right here. So remember, like charges repel and unlike charges attract. These are unlike charges, like charges, right? So like charges repel, correct? Repel. Let's move the charge another position, right? It's gonna be repelled. Another position right here, right? It's gonna be repelled. Right here, right? It's gonna be repelled. So how the field, the electric field of this positive charge looks like? Well, in this way. So positive charge, it has an electric field that goes out right from this charge, positive charge, correct? And this is the electric field. These lines are also called line of force. Line of force. Correct? Perfect. Now what happens if we change this charge by negative charge? Well, we repeat the same steps. Again, this test charge is a positive charge, but in this case, they attract, right? So this charge is being attracted by the test charge being attracted by this charge, correct? So it goes in that way. Perfect. So how is the electric field for this negative charge? Well, it goes in this way, right? In this way. In this way. And again, these are the line of force, and this is the electric field for a negative charge. What happens when we place together these two charges? Okay, let's do it. In this case, we have this arrangement. This is positive and this is negative. Well, remember, the lines are leaving the positive charge, so it's gonna be in this way. It goes from positive to negative, correct? From positive to negative in this direction. And the electric field in this case is tangent to these lines, right? This is the electric field. Electric field, correct? Right here is tangent and tangent, right? At this point is tangent, and so tangent to the lines of forces. You see it? Okay, great. Now let's try to find a formula that helps us to represent the electric field. Well, imagine one more time that we have a charge right here. Imagine it's a test charge. And now we apply the Coulomb's law. Coulomb's law says that the magnitude of between two forces, right, is equals to, between two charges, is equals to K, Q1, Q2 over R squared, right? This is Coulomb's law. We have two charges. This is the test charge. This is any charge right here, correct? And then what happens? Well, we have an attractive force, but we're looking not for force. We're looking only for the electric field. Now, if we remove this charge, correct, there is no force right here, but the electric field is still present there, even though we have no charge. The charge is used just to find this force, but if there is no charge, still the electric field is present. So let's use this charge just to specify the force or specify the presence of electric field, and then let's remove it, right? And this is done in this way. So the electric field, right, as a vector is equals to the force divided by the test charge. And this is the definition for electric field, correct? So what do we have right here? We have the electric field. Let's use the magnitude, the same thing as for the Coulomb's law, is equals to force divided by the test charge. Remember, the test charge is always positive by convention. Perfect. Now, we can also continue in this analysis, correct? We can say that the electric field, let's use only the magnitude in this chapter. So what is force using Coulomb's law? KQ1. Now in this case, one of them is gonna be this charge. Remember, we use the magnetic field right here, correct? And the electric field. The electric field right here, and we have the test charge right here, right? Charges, correct? And we have the force. It's gonna be Q naught over any charge right here, over Q naught times what? Times R squared. So what should be then the electric field using Coulomb's law? Well, electric field is equals to K, right? What else? Charge divided by R squared. Perfect. Again, this is for point charges. For point charges. Great. So I'm gonna call this is the magnitude. So magnitude and magnitude. Correct. What should be the units for the electric field? What should be the units? But we can go back to this formula. So electric field unit is gonna be units for force, newtons. Units for the charge, coulombs. Correct? Perfect. Also, let's do the same thing as we did for charges. We have different charges. What should be the net magnetic field, electric field? Okay, let's do it. The net electric field. One more time. Remember, these are vectors. Forces and electric field are vectors. Remember, we have a vector. Any vector, let's say force, y is equals to the sum, right? The component in the direction plus the sum, correct? In the y direction, y hat, right? Y hat. The same thing for the electric field, correct? As a vector. The sum of the component in the x direction plus the summation, right, of the component in the y direction. Y hat. Correct? And we can find from here, remember, magnitude and direction. Okay, perfect. Imagine that we have, one more time, two charges. I need two charges. One charge right here, another charge right here. Imagine for simplicity. Okay, this is x direction, this is y direction. We have another charge right here, correct? Let's call this charge 1 and let's call this charge 2. Okay, for simplicity, let's take this to be positive 2 coulombs. This is negative 2 coulombs. For simplicity, you can change the values. And we're looking for the electric field at some point. Imagine one more time, 3, imagine right here. It's gonna be this point P. Let's find the electric field at that point. Again, this is 1, 2, 3, 1, 2, 3, and 4, for example. These are distances in meters, correct? Meters, right? Y is also meters. Right. How we can find the electric field at this point? Well, it's gonna be the electric field produced by this charge plus the electric field produced by this charge. Okay, what happens in this the electric field produced by this charge? Well, because it's negative, it's gonna be toward the charge, right? So we have an electric field right toward the charge. Imagine this is the electric field produced by charge 2. Okay. What about the electric field produced by this charge? Well, it's gonna be, in this direction, correct? So this is the electric field produced by charge 1. Now, what should be the net electric field? Well, this vector plus this vector. We can approximate, right, this one in this way, correct, using the parallelogram technique. So we expect is this in this direction? No, this is going outward, no wonder. Excuse me, this is not this way, right? This is being towards away. Okay, perfect. Look, away. This is gonna be the electric field produced by this charge. Okay, perfect. Wait, I can't believe it's not this way. It was out from the charge, and this was toward the charge. Perfect. One more time. If this is the electric field produced by this charge, well, we can approximate more or less to see what happens. Right, what should be the net or the sum, right, electric fields. In this case, the electric field net is equals to the electric field produced by charge 1 plus electric field produced by charge 2. Correct, and then we can use this equation right here, we can use this one. Okay, so what should be the electric, also remember we can use component, because we're in 2D. So the electric field, right, in the x direction is equals to the electric field in the x direction for this field plus in the x direction for the other field. Okay, perfect. Let's do it. The electric field produced by charge 1. Remember, breaking into component. This is angle theta. We need to know this angle to do it correct, and then we have. Let me erase this part. Component in this direction, correct. This is a component in that direction. Perfect. So it's gonna be what? It's gonna be B1 cosine theta, correct. What else? This is for charge 1. For charge 2, well, charge 2 has only in the y direction. Perfect. What about in the y direction? In the y direction, well, we have that this has component in the this 2 has component in the y direction, correct? So we have E1 sine theta, correct, minus what? Minus this one goes down. Is gonna be using this equation one more time. Using this equation right here is gonna be E minus E2 magnitude, because it goes down. And then we can substitute the values, right? For example, it's equals to what is E1? E1 is gonna be KQ1 divided by R1 squared. What about for this one? Well, what is E1 again? It's gonna be KQ1 over R1 squared. Right, well, this is R1, right? From here to here is R1. R1 is equals to what? 5, right? 5 meters. Okay. And then what else? Sine theta. Well, we need to find the sine theta right there. Minus E2, right? It goes downward in the y direction, and this is equals to KQ2 divided by R. Okay, this is R1, right? Not R2, it's R1, correct? No, this is R2, right? R1 is R1. Okay, R2, right? No, it's not R2, it's R1. Come on. R1 squared because it's E1. Okay, it's gonna be R2 squared. Perfect. And then we substitute the values, and we get the answer. Got it? For example, one more time, imagine that this is what? This is let's say 5 newtons per coulombs, right? Imagine that this is another number. You have to calculate it, right? Let's say 3 newtons per coulombs square. Coulomb square. That's the unit for the electric field. No, per coulomb. What's coulomb square? Newtons per coulomb, right? newtons per coulomb, what should be then the electric field? Using the vector notation, the electric field as a vector gonna be 5 newtons per coulombs, right? X hat, right? X hat plus what? Imagine this is correct. Again, you have to substitute the values from here to find the right answer. 3 newtons per coulomb, right? Y squared. And this is the vector representation for the electric field. Also, later we can find the magnitude. Remember, when we have a vector, the magnitude is equal to square root of this component, the square plus this component in the y direction square. Also, the angle, right, which is the direction, is gonna be the tangent inverse, correct? Tangent inverse of the component in the y direction, electric field in the y direction over the component in the x direction. Right? It's just coming from this analysis. Again, this is called the principle of superposition. That is used using again charges. Correct. Perfect. Now let's see what happens when we have a conductor and an insulator. What's the difference? Okay, look, when we have a conductor, like metals, right? Metals are conductors. Imagine this is the conductor, and it's neutral. What happens if we charge this conductor? If we charge this conductor, say by contact, what happens? Well, the charge is distributed, right, uniformly through the sphere. You touch, imagine this is charged. We touch it and we charge it. So the charge covers all the surface of the conductor. What happens if this is non-conductor or insulator? Non-conductor. Well, we touch this object by this, which is charged. We touch it. So we charge it. Yeah, we charge it, but the charge stays in one place, imagine. It doesn't cover the whole surface. The charge is not conducted. Right here, we place it right here, the charge is conducted and cover the whole surface. Right here, the charge stays there because it's a non-conductor. Okay, perfect. Now, imagine that we have, again, a sphere, solid, right? If the sphere is solid, and we introduced by some way negative charges, and we place it inside, right? This is a conductor, right? What happens with the charges inside? The charges repel, right? Because a conductor, they can move from one place to another place, and the place that they are placed is the farthest as they came from each other, right? And why is that position gonna be on the surface? So for electrostatics, right, a charged object, the extra charge, the excess of charges, right, is on the surface of the conductor. Okay, perfect. Now imagine that we have a sphere. It's actually a shell, but a shell. The sphere is not solid, but it's just the shell, a spherical shell. Imagine it's this one. And again, we charge it. If we charge it, as we know, the charges stay at the surface. At the surface. Correct. Now, what happens inside? What should be the electric field? What should be the electric field inside? Well, imagine that we are the center, correct? So we have forces, the force produced by this charge at this point, or the electric field actually, right? At this point, right, it's gonna be in this direction, at this point in this direction, right, and so on. So these are opposite because they are the same distance, they have the same magnitude. So the center, the electric field is 0. Okay, now what happens if we will move this charge right here, or the points right there? What happens? What should be the electric field there? Well, look, these charges act on this point, and let's take this one right here. And also these charges, correct, act on that point. Also, we can make another cones right in this direction. But let's take that part. Right here we have less charges, but the distance is less. Remember, the formula is this one. The electric field is equals to K charge divided by R squared. The charge right here is less than the charge right here, right? But the distance is less than the distance right here. So it's found that at the end, correct, the electric field is also equals to 0. So the electric field inside of a sphere, the conductor could be solid, or could be a shell, is 0, right? The electric this must be a conductor, okay? So the electric field is 0. If the electric field is 0, what happens to the force, right? The force must be 0, the net force. Actually, we just pay attention to the electric field, correct? Okay, perfect. Now, also for electrostatics, when we're dealing with electrostatics, imagine that we have a surface, any surface like this, any surface, and we charge this surface. Let's imagine it's positive, right? So, and we're looking for the electric field. Imagine that the electric field goes in this direction. Remember, we're dealing with electrostatics. Charges are rest. If the electric field goes in this direction, means that we can break this into components, one in this direction and one in that direction. Correct? The electric field, or the force, remember, because the electric field is in function of the force, so we have a force in a direction. This force is being stopped by this plate, let's say, by this material. But what about in this direction? Now the charges, if they feel a force in this direction, these charges move. But the condition is what? This is supposed to be at rest because we are dealing with electrostatics. Correct? Means what? In electrostatics, the forces or the electric field must be perpendicular to the surface, right? So the electric field must be perpendicular. Because if the electric field is not perpendicular, there is a component parallel to the surface, and that produces motion. And that contradicts our statement. The charges must be at rest. If the charges must be at rest, the electric field must be perpendicular to the surface where the charges are. Got it? Perfect. Okay. Another example is this one. Look, imagine that we have, one more time, this is two plate. These are two plates. Imagine this is positive charge and this is negative charge. Usually they have the same, when we have two plates like this, they have the same charge. But one is positive, one is negative. What happens? Well, how is the electric field between these two plates? Well, remember the lines of force, or the electric field must be perpendicular to the surface, right? It's gonna be perpendicular, 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 perpendicular. Correct? And according to our convention, the lines of force leaves positive charges and goes to negative charges. Correct? So this is the electric field. And as you can see, this is a constant electric field. It's very important. Correct? It's constant electric field. How we can know it's constant? Well, because the lines are parallel. When we have a field and the lines are parallel, the same kind, right? The field in this case is constant. Correct? Perfect. Now imagine that we place in between we place a conductor. What happens if we place a conductor right here? A conductor. Well, now look, if we have a line coming, it must be perpendicular, right? We have another line right here, gonna be perpendicular to the surface. Another line perpendicular to the surface, correct? Another lines of force or electric lines, right, gonna be perpendicular, right, and so on, correct? Something like this, but it's little perpendicular, right, perpendicular, and so on. Perpendicular, perpendicular, correct? And how is the electric field inside? The electric field, right, is gonna be 0. Is equals to 0. Remember, we're dealing with electrostatics. All of this analysis is with electrostatics. Okay, electrostatics. Perfect. Great. Now let's go to the last topic for this chapter. The last topic is gonna be Gauss's law. Gauss's law. Okay, look, in this analysis we introduce the concept of electric flux. Electric flux. The symbol is this. Let's say electric flux. In this case, we take the electric field like a fluid, right? A flow, right? That flows, a substance that flows. That's why it's called electric flux. Imagine that substance is like a rain. Imagine you have rain. Okay, this is the rain, but actually we represent this as the electric field, right? The electric field is going down. Okay, perfect. And imagine that I want to collect this field using a funnel. Okay, that's the funnel, right? That's the funnel. I have to catch it with this funnel. This funnel has an area, right? Has an area. This is area. Look, when we have an area and a vector right here, we take this area as a vector in this way. Look, this is the surface, imagine. This is the area, and this is the direction, correct? This is the magnitude area, and that's the direction. That is in the normal direction, right? This is normal direction. Remember, we covered this in the previous physics 2A. Those who are taking this is physics 2B, physics 2A. Remember, we use a surface. We have an object, and we call this, right, the normal force. Remember, this is the normal force. The normal force. The same thing happens over here. This is the normal. It just indicates the direction. Correct. So in this case, we have then that this is the area, but it behaves as a vector too. It has a direction, right? That's the direction. It's perpendicular to this surface, but it's parallel in this case to the electric field. Okay, this direction. Perfect. Now what happens? Look, let's find the magnetic flux, the amount of, in this case, field going through this opening to this surface. And we can see that this electric flux is proportional to the electric field, correct? If you increase the amount of rain, right, when harder, right, we collect more rain, we collect more electric field. Perfect. Also, if we increase the area, also we increase the amount of the electric flux being collected or going through the area. Got it? But what happens when we rotate the funnel? Right? When it's parallel, we have the maximum, but when it's perpendicular, it's gonna be 0 zero electric flux going through this surface, right? We rotate it, what's gonna be zero. So means that also this electric flux depends on the angle, right? Which function give us when is zero angle, which when they're parallel, they're zero angle is the maximum, and when the angle is perpendicular is zero. That's gonna be sine, right? So this sine or cosine? Cosine, right? When these two are parallel, what is the angle? Zero. Cosine 0 is 1. That's the maximum. When it's perpendicular, right? What is the angle? 90. Cosine 90 is 0. With 0, right? When we rotate the funnel. Okay, perfect. So this is also proportional to cosine theta. Correct? Perfect. Now, let's combine all of these three quantities, right? These two quantities plus the angle of cosine. And what do we have? We have that this magnetic flux, electric flux is proportional to area, electric field, area cosine theta. Let's eliminate this symbol using a constant. It's found that the constant is 1 because we're making the units of this quantity the same as this unit. So K, the constant of proportionality is 1. Okay, so what do we have? This electric flux is equals to electric field area times cosine theta. Okay, this formula is very, very important too. Okay, this is the electric flux is equals to electric field area cosine theta. Look, this angle should be between the direction of the electric field and the direction of the area. Okay, perfect. Now, Gauss's law says that also, look, also this electric flux is proportional to the charge. If we increase the charge, we're dealing with point charges in this case. When we increase the charge, the magnitude we increase the lines of force. We increase the electric fields, correct? If we increase the electric field, right, we increase also the electric flux, correct? So how do we eliminate this symbol? Using a constant. In this case, the constant is just epsilon naught, correct? But what is now, one more time, the electric field? The electric field is this one. So when we combine these two, the electric flux is this one, right? So when we combine these two, what do we have? We have that the electric field times the area times cosine theta is equals to the total charge enclosed by the surface divided by epsilon naught. And this is Coulomb's law. Gauss's law, right? Gauss's law. Correct? When we apply this to, we create surfaces, we have area right here. For example, when we have this point charge, right? This is the electric field, right? That's the electric field. Now we create a surface. We call this the Gaussian surface. Gaussian surface. The surface depends on the symmetry, right? But to make symmetry, this is as a point, we create a sphere. If this is a wire, right? A wire, we create a cylinder, right? By symmetry. And this is a sphere, we create another sphere. If this is a plate, if you have a plate, we create another cylinder like this, right? A cylinder. So it depends on the distribution of the charge. Alright, in this case we have this point charge. Okay, for this point charge, right, we use again the Gauss's law to calculate the electric field. Remember, we have another way how we can calculate the electric field using Coulomb's law. This one, Coulomb's law. These two, right? But in general, this is harder to do it than in this case. This is much easier. Okay, for example, what do we have right here? Look, we can find the angle between the electric field and the surface. This is 90 degrees, correct? 90 degrees, is that the angle? No, it's not the angle 90 degrees. Look, remember we take a surface right here, any surface right here, right? This is the direction of the surface and this is the direction of the electric field. This is the area, so they're parallel. They're parallel, correct? Cosine 0, because when they're parallel, right, the angle is 0, so cosine 0 is gonna be 1. So what do we have then? So according to Gauss's law, this is electric field times the area is equals to the total charge in this case enclosed by the surface divided by epsilon naught. And then we solve for the electric field. So the electric field is equals to charge, right, divided by area epsilon naught. And what is this? Well, we can go back, right? And when we substitute the value for the area, in this case the area is the area of a surface, right, a spherical surface, and it's equals to what? Charge over 4 pi squared epsilon naught, which is the same as, I erased that part. Of course, coming from, well, I think I put it right here, correct? I remember from the previous video, we found that k is equals to 1 over 4 pi epsilon naught. When we substitute this value, what do we have? This is k, this is the charge. Look, this is the charge divided by 4 pi epsilon naught times r squared, which is the same as this one right here, correct? The same as this one right here. And we create the same result by using Gauss's law. Okay, now let's apply again Gauss's law for the next case. Imagine that we have one more time a two-plate system. This is one plate, another plate right here. Correct. One more time, it's positive, and this is negative for simplicity. Okay, they have the same area, the same charge to make it easier. Correct. Now, if we take only one plate, okay, this plate, remember, is positive, so the lines, right, of force go in this direction, right, in both directions. Right? This is for, this is passive, correct? What about when it's negative? The same thing, it goes, correct? Now toward the charge, it's negative, correct? Okay, perfect. Now let's combine these two. And what do we have? Well, we have the lines produced by these plates are this one. And the lines produced by this plate are this one. Wow, can you see it? So we have twice, right? Twice this amount. So what do we have? That the total electric field inside is the electric field positive plus the electric field negative, right? But this is equals to what? Twice, because they have the same charge, twice that charge. That's electric field, right? This is the electric field right here. But according to Coulomb's law, what is Coulomb's law? Oh my, I erased it. This equals to what? This is equals to, remember Coulomb's law says that the electric field times the area cosine theta is equals to the charge over epsilon naught. Right? Why the total charge? This is the total electric field. So what do we have? 2 times the electric field is equals to charge over area epsilon naught. But look, when we're dealing with plates, remember this symbol is usually for, in this case, for point charges. But when we're dealing with surface, with solids, could be a surface, could be a string, could be a volume. We don't use this quantity, we use densities, right? We have, for we're dealing with charges, we have these three types of charge density, right? We have linear charge density. We have surface, it's a surface, right? It's a plate, surface charge density. We have volume charge density. The symbol usually is lambda, right here is equals to the charge over L. Right here, the symbol is sigma equals to charge over area, correct, over area. And right here is rho, is the charge over the volume. Right here we're dealing with plates, right, with plates. So we use this symbol. In this case, what should be the charge? Look, charge is equals to sigma times the area. Okay, let's place this value right here. And what do we have? The charge, which is sigma times the area divided by area epsilon naught. So it's cancelled. What do we have? The electric field inside of these two plates is equals to sigma over 2 epsilon naught. Right? So this is equals to sigma over 2 epsilon naught. This is very important because this is actually the shape for a parallel plate capacitor. I have to cover this later. Okay, parallel plate capacitor. A capacitor is a device that stores charge and electric field. Right, like in this case, this is a capacitor. And this is the electric field, it's sigma. So this is the charge density divided by 2 times epsilon naught. Okay, great. And with this we finish this topic, this chapter, right, related to electrostatics. And see you in the next chapter. Thank you. Bye.